Good morning, Year 11. Today we're going to look at how to use bond energies to calculate the energy changes in a reaction. The first equation we're going to start with is the combustion of ethanol. So here we have the formula for ethanol. It reacts with oxygen to form carbon dioxide and water. Another way to look at this reaction would be the displayed formula, which we have here. So this is useful to us because it shows every single bond that exists in all of the molecules we've got used in the reaction. We've also got coefficient in front of some of these molecules. So for example, if we have a look here for oxygen, because there's a 3 in front of this, it means there are 3 of these molecules present. In a reaction, when it takes place, we assume that all of the bonds on the left hand side of the equation are broken, and then all of the bonds on the right hand side of the equation are made again. And we can use bond energies to work out how much energy is going to be needed to break all of them and how much energy is going to be given out when we make all the ones on the right hand side. So just remember from last lesson that if you're breaking bonds, you're taking energy in. If you're making bonds, you're giving energy out. So let's have a look what we have to do here. So in the little first box where it says bonds broken, we're going to look at every single bond we've got here, how many of them we have, and then how much energy each of them is worth. So the first one on our list is CH. So this is a carbon bonded with a hydrogen. So in my box I'm going to draw this bond. I'm now going to record how much energy one of those bonds has. So that is 413 kilojoules. I'm going to need to go over here and count how many I've got. So 1, 2, 3, 4, 5. Yeah, I've got 5 of those. So at some point I'm going to need to multiply the bond energy times the number of bonds I've got. We'll do that in a moment though. So next I'm going to look at carbon-carbon bonds. I've only got 1 of those, so down here I'll draw carbon-carbon. That is worth, or that has 347 kilojoules. I've only got 1 of them, so I'll multiply that by 1. The next on the list is CO bond, and I've got 1 of those as well. 358 times 1. Next on the lists, well, I'm going to go for this one next because I haven't done it yet. So that's an OH bond, and that is 467 kilojoules, and I've got 1 of those as well. So that's every bond from our ethanol, from the first molecule. Now we need to have a look at the second molecule. So the second molecule is an O2 molecule, and in each molecule we've got 1 of these O double bond O molecules. So if you've got 2 lines like this, that means a double bond. If you've only got 1 line like we did over here, that's a single covalent bond. So we have 1 oxygen double bond. Each one of those has an energy of 495, but there is 1 area we could make a mistake here. Look, so there's a coefficient in front of this oxygen. So every molecule has 1 of these bonds, but there are 3 molecules. So we have to multiply this 495 by 3. Next, we need to do our sums using a calculator. So 413 times 5. That gives us 2065. And all of these are just times by 1, so that's pretty straightforward. And then lastly we've got our oxygen, 495 times 3. That gives us 1485. And the last thing we need to do is add all these values together. So I had 2065 plus 347 plus 358 plus 467 plus 1485 gives me 4722, and that's kilojoules per mole. So if I want to break all of these bonds, then I need to supply 4,722 kilojoules of energy for every mole of this substance that I want to break. Don't worry too much about the units today, that's not something we're going to focus on. Just know that we need to provide this much energy to break it. So we've dealt with the left hand side of the equation. Now the next thing we need to look at is the right hand side of the equation. So these are the bonds that are going to be made. I've got carbon dioxide here, so we have one carbon, and that carbon is bonded to two other oxygen molecules, and that is each with a double bond. So if we look at the oxygen to carbon double bond, it's here in our table. Each one of those has 799 kilojoules per mole of energy. There are two of them in every molecule, and there are two molecules, so 2 times 2 gives us 4, and the other molecule we have is a water molecule that's got an OH bond, and each of those OH bonds we can see here has 467 joules. We'll count them. Every molecule has 2 of these bonds. There are 3 molecules. 3 times 2 is 6, so that's going to be times 6. Calculators out again. 799 times 4 gives me 3196. 467 times 6 gives me 2802, and then we add those two together, gives us 5998 kilojoules per mole. And again, don't worry too much about the units. So we can just look at this straight away. The energy that we need to put in to break all the bonds is 4,722. The energy we get out from making the bonds is 5,998. So we can see straight away that this number is bigger than this number. So we're giving out more energy than we're taking in. So this is probably going to be an exothermic reaction. Let's do the maths. So our energy change is going to be the energy from the bonds that are made. So start with this one minus the energy of the bonds that are broken. So we had 5998 minus 4722. Pop that into a calculator, and that gives us 1276 kilojoules per mole. So 1726 kilojoules per mole, and this energy is given out, and it's exothermic as the energy released when the bonds are formed is greater than energy taken in when the bonds are broken.